Good evening. I'm Chris Brown, the Deputy Director here at the Smithsonian's National Air and Space Museum, and it is my pleasure to welcome all of you to tonight's installment of our Exploring Space lecture series. As you may have noticed when you came into the building this evening, we are in the middle, or certainly at the beginning, of a major project to transform our building here on the National Mall. But before we jump into the program, I do want to share with you our vision for this very large renovation.
It begins with a spark. Passion for air and space.
Hey, Jackie, wait for me.
The passion for air and space.
Why don't you take it? You look better on you anyway.
That passion can grow.
Hey, Jackie.
Lighting the way forward for a lifetime. And now, with the monumental transformation of the Smithsonian's National Air and Space Museum, this place that has ignited generations of imaginations will be completely reimagined, inside and out. Also, this museum can be even more of what it's always been, a place that gives life to a remarkable past and gives rise to the people who will make history tomorrow. Join us in the mission to transform the National Air and Space Museum. Together, we'll ignite tomorrow.
Yes, that's Harrison Ford that did the soundtrack for that. He's a wonderful friend of the museum, and we are privileged to have him join us in this effort. When we have finished redesigning and updating all 23 of our galleries, the new National Air and Space Museum will tell the transformative stories of aviation and space in new ways to new audiences, allowing us to reach further than ever before. It will provide the inspiration to our visitors that will encourage them to achieve the next great milestones in aviation and space. We are a year into this 7-year renovation, but don't worry, we'll be staying open throughout the whole project. So we invite you to continue visiting and attending events like this one, even if you see cranes and fencing outside. We'll still be here to share the stories of aviation and space like the one Jim will share with us tonight. Our renovation is just one of the big projects underway at Air and Space this year. Another is our celebration of the upcoming 50th anniversary of the Apollo moon landing. Tonight's event is part of that ongoing Apollo 50th celebration. This year's Exploring Space series is focusing on the moon, with a look at lunar science and exploration through the years and into the future. Tonight's program is made possible by the generous support of our sponsors, Aerojet Rocketdyne and United Launch Alliance, companies that have been instrumental in launching, propelling, and landing many spacecraft that have explored our solar system. Representatives of these organizations are here in the audience tonight. Please join me in thanking them for their generosity in supporting this great evening. And we are delighted to have Dr. Jim Green with us here tonight to talk about the future of lunar exploration. I know I'm cutting into your time, but it is bully pulpit. I am going to take a moment to introduce you. Jim has worked for NASA for nearly 40 years, and in that time has run the National Space Science Data Center and held other administrative positions while serving as a co-investigator and deputy project scientist for the Image Magnetosphere Research Mission. In 2006, he became the director of NASA's Planetary Science Division, and in 2018, he was appointed as NASA's chief scientist, something he has in common with the director of this museum, Dr. Ellen Stofan. Jim is a tireless advocate for planetary science, and we are excited to hear his thoughts on how the moon provides a natural yet challenging environment for the next generation of robotic and human explorers. It is now my pleasure and privilege to introduce to you Dr. Jim Green.
Thank you very much, Chris. Thank you very much. Indeed, it's just a delight to be here to talk about the future lunar exploration. And so let's get started. Bring up my first slide. What indeed I want to talk about today is really our plans for the future of exploring the moon, both scientifically, but also human exploration. And so it's robots and scientists, etc., working together. Now, in order to do that, because as a scientist I'm bound to do this, we need to talk about what we've learned about the moon, because indeed our future lunar exploration builds on the past. So what we're looking at here is the start in the 60s of lunar exploration. And of course, that was the United States and the former Soviet Union really going at it with all kinds of missions. The group at the top are those that are flybys, and then the next group are orbiters, and then of course you see the landers. And what happens over this time period is an enormous number of missions on both sides. And what you get out of this immediately is NASA doesn't do Star Trek. They don't do go where no human has gone before. You know, why don't we just send humans there, right? So what we do are a variety of precursor missions. So it's the planetary scientists that become the pioneers that go out and are analyzing the data and creating instruments and going to the moon. And in fact, out of this set, before the Apollos first showed up, we had on the order of 25 or so precursor missions, all right? So we did a lot of work, a lot of mapping. All that led to, of course, our 50 years ago this year, the landing of Apollo 11 on the moon. And so we have Neil Armstrong, Mike Collins, and Buzz Aldrin. Buzz and Neil, of course, were on the Eagle when it landed. And one of the first things that Neil did when he walked out of the Eagle, and before he really got going down the ladder, is he leaned down and he looked at the lander legs, all right? And the reason why is a lot of planetary scientists at that time said, okay, with so many craters on the moon and so much ground up rock that we call regolith, really tiny pieces of these silicate rock all over the place, you may end up sinking into it chest deep, all right? Well, that's a game changer. That would end a mission in a minute. And even though we had surveyors and rangers that had landed on the moon and did a variety of science, and we never saw that, it didn't mean there were areas where this material may have piled up for some unusual reason. And so what Neil did, of course, is he leaned out and he looked down and he said right away, it doesn't look like the lander legs have been depressed more than an inch. You know, I'm paraphrasing it, but you know that was already the start of the science in the area. So once Neil and Buzz both got out, they started to deploy a variety of instruments. Now, the instrument that you see right in the front, in the center, is a seismometer. So we really didn't know much about how the moon is made up. Now, we've done seismic measurements on Earth. We know the Earth has three basic parts: a crust, a mantle, and a core. A core is always where the heavier material sinks, because you've actually heated the whole planet and mixed everything up such that the heavy stuff sinks and the lighter stuff floats to the top, okay, and creates these layers. So we wanted to know, well, what's the moon? You know, what's the structure of the moon? How big is the core? How big is the mantle? How big is the crust? And so a seismic instrument, you know, is the ideal instrument. Another one that's actually hid in this view that you now can see from this angle is a passive instrument. It didn't need electricity to operate. It's actually a 1.5 by 1.5 square of reflectors, And what we were going to do with that is we were going to measure the distance between the Earth and the moon. And how you do that is we take a laser, point it right at the reflector, fire it, get the light reflected, come back, time it. Okay? So if we can time it, then we know how fast light travels, then we're going to get the distance. Apollo 11, 14, and 15 all had them. Okay? So we have had retroreflectors out on the moon for 50 years. And every year, we hit them with laser light. And we know the distance from here to the moon. Now, why are we doing it every year? You know, didn't we get it right the first time? Well, we're finding out it's changing. Okay? The moon is moving away from the Earth about 1.5 inches a year. Okay? And so that makes us want to continue to do that kind of observation. One of the important observations of the moon that you actually have to factor in when you talk about how the moon was created. So here are the 6 Apollo missions that made it. Of course, 13's not on it. And you have 11, 12, 14, 15, 16, 17, and where on the moon they are. They're all on the near side. Okay, they're all on the side we can see. They're all at a place where we actually had communication. Okay, that far side of the moon, we wouldn't want to go because we'd have no ability to communicate. So we wouldn't want to do that for a long time until we actually have the ability to have the communication on the far side. And so this was a fantastic set of missions for which they deployed instruments and they brought back lunar material. So more than 840 pounds of lunar material was brought back from those 6 missions, okay? And we manage them at Johnson Space Center in Houston, okay? NASA's got 10 centers and they all have certain responsibilities. Houston is the man, what we call man, but you know, human exploration is there. There are both men and women in the astronaut corps, of course. And the curation facility, here's a nice look at it. You know, so the samples are under nitrogen. They're well taken care of. This is a fabulous facility. And indeed, we've been holding these samples and will continue to do so since they were brought back. Now, it turns out we haven't analyzed all the samples. We're holding back at least 60% of the samples, okay? We characterize them, we talk about them, we photograph them, we get some basic information, we put that in a database, it's online, but in reality, we don't allow analysis of all those samples. We allow analysis of a certain set of samples, and the community, scientific community, put in proposals saying this is what we want to do, we want to look at this, we want to analyze this, and really dig into what we see, and that's been going on for 50 years. And it's doing nothing but accelerating. We're finding out more and more about the moon and about the history of the Earth-Moon system from those samples. And we're getting better at it. One of the reasons why we don't analyze all the samples all at once is indeed the laboratory equipment is only getting better, okay? And so we can peer into these rocks, we can look at the mineralogy, we can get high-resolution imaging, and we can get the composition and what are called isotopes. You know, so there are different flavors of carbon, different flavors of oxygen, you know, because they have different compositions of neutrons, number of neutrons in the nucleus, and those are called isotopes. But out of these samples, we've learned a whole bunch. One of the first things we learned is the moon is old. 4.5, 4.6 billion years old. That was a surprise, because when we run around the Earth and we grab old rocks from the Earth and we take them in the lab and we analyze them, we get about 3.8 or 3.9 billion years, okay? We don't get 4.6. So why? Why is there a difference between the age of the moon and the age of the Earth based on the age of those samples? And it turns out on Earth, because of plate tectonics, because of our oceans, because of our biosphere, our surface is modified all the time. And it's only in a couple regions, one in Australia and another one in Greenland, where we can find these really old rocks. And even then, they're only about 3.8 or so billion years old. Another aspect of what we're finding out is when the moon came into being, it was molten rock on the surface. We call that a magma ocean. And when that cooled, that created the crust. Now what's underneath that crust is under higher pressure. It is indeed what we'd call today the mantle, and it would also be molten rock. But at least that outer crust is cooled. And indeed, when we go to the moon and bring back samples, we can actually bring back these early samples, and it tells us that that's how the moon started out, with a magma ocean everywhere. The big process that really changes everything about the moon is the cratering, is the impacts. Now, what's really fascinating when you look at the history, prior to Apollo, we were really confused about what we were looking at. When we see these indentations, okay, with peaks in the middle, and we look at analogies on Earth, that could be a caldera. And in fact, many planetary scientists thought that the moon had all these volcanic vents associated with them, okay? And some scientists in the 60s started the process of convincing everyone those are not volcanic caldera, they're impacts. They're impacts from a variety of sizes. Some are really huge, some are smaller, and then you have this variation. So once the crust cooled, then the big process are the impacts, okay? And so those impacts, okay, now we're going to get a history. Because once you have an impact, and that impact then destroys the rock, it recools, we can actually take the rock and date it from the time it started that process of becoming a rock again. And then we can date each and every one of those impacts. And now we have a history of the moon. So that was incredibly important for us to do. There's also, when we brought back these rocks and started to date them, it gave us an indication of some areas being older than others, okay? And in fact, these dark regions on the near side, we call basins, are actually impact regions, okay? These are huge impact regions. Once they get above about 300 kilometers, we don't call them craters anymore, we call them basins. But after you have this huge impact, what happens is the magma then comes in and fills that in. And it's dark. So what we see when we look at the moon, the dark Mare, that's actually magma that has occurred from these huge impacts after the moon was created and cooled for several hundred million years. So dating those then is kind of neat, and really revealing what happened to indeed the solar system. And so when these samples were brought back and we brought them into the laboratory, we then looked at them, and one of the things that we want to look at is there any water in them, okay? We couldn't find any water. Today, our instrumentation is so good, we actually can find trace water in it, in these samples. But at the time, the end result of that is, oh, the moon is absolutely bone dry. absolutely bone dry, okay? So that was always something we talked about. So therefore, that meant that, you know, without water, you don't have life, and so you can forget about that, and so we can let the astronauts out of the trailer. And, you know, and that was always very good to know. The key thing that we found out by looking at these rocks are they are like Earth, and therefore the moon and the Earth must have a very tightly coupled origin. You know, they're the same type of material, all right? As I mentioned, when we brought these samples back and started to date them, we'd come from different areas. Sometimes we'd get them from areas where there'd be a lot of craters, and the date would be older, okay? Sometimes you'd get them from areas that were lightly cratered, and those rocks would be younger, okay? And once again, remember, after an impact, you melt the rock, and when that rock then cools and becomes a rock, that's when the clock starts on that new rock, okay? And we can determine that. So this told us that there's a history of impacts going on at the moon, and that turned out to be an enormous benefit to planetary scientists because it's a chronometer. When we look at other impact regions and we see these large regions that have huge amounts of crater, those must be older. And then we see areas where there's a few craters, that must be newer. And then that tells us about planetary processes. And we've used this idea of having a chronometer all over the place in the solar system, all over the place. So where are the craters on Earth? If we see craters on the moon, where are they on the Earth? Well, the Earth's biosphere has eliminated most of them. There are some telltale signs, you know, and as actually the Greenland ice sheet starts to wane, there's some huge cratered areas underneath the ice sheet that we're starting to see, okay? So our biosphere is literally destroyed, and our atmosphere have really destroyed those features. So what we're finding out then, just by size alone, that for every one crater on the moon, there's 20 craters on the Earth, okay? Just by size alone, all right? So that means all kinds of material came to us. Well, what kind of material? Well, if we go to the moon, we can get that idea. We can understand over time what came to the Earth. We can understand if there was a time where life got seeded on this planet. And that answer is from rocks on the moon, okay? So what happened after 1976 was a hiatus, all right? Planetary science turned its attention to many other bodies, and it wasn't until the 1990s when the Japanese launched Hiten that then new missions started coming. But it wasn't just the US or the Russians. It was the Chinese. It was the Japanese. It was India. And so a whole host of missions started a new era of lunar exploration, separated by more than a decade, okay? Now, sometimes that happens because we get a glut of information and we just need time to understand it, analyze it, and work on it, okay? And then we can determine what the next set of important questions we want to answer and then go at it, okay? And that definitely happened to the moon. Whether that's the total reason or not, it's certainly one of those. But this new era of missions, now, because we had the Apollo samples analysis and the Rangers and the surveyors and all the other precursor missions, all that information coming in, we now knew what we wanted to do next, and those missions did a fantastic job. And so I want to tell you a little bit about that new era of exploration. So here's the moon from LRO. The near side is what we see, of course. The moon is tidally locked. So in 1 month period, it's always pointing that one face to us. So if you just looked at the moon, it spins, okay, and it spins in a month. And that month matches the month that it takes to go around, the 29 days that it takes to go around the Earth. Now you see these dark spots, they're only on the near side. Okay, so we have to explain that. You know, that's got to be part of our understanding of how the moon came together. And on the far side, what we see is actually only 3 or 4% of that far side has these mare. Okay, so that means those impacts weren't deep enough to bring up the magma that then filled those craters in, that then gave you that darkish view of the moon. So that magma contains a variety of iron and what we call high Z material, you know, nickel, iron, and then that causes a completely reflectivity associated with it, which makes it look darker than the normal old crust of the moon, as you can see there. LRO did another spectacular thing. It was had a laser that fired down to the surface, came back up to the spacecraft. We could time it, therefore we could figure out the distance, and that allowed us then to put together a height distribution. Okay, so this now is the moon colored in height. So the red and the white are the highs. Okay, and the purples and the blues are the lows. So what you see on the near side, you know, you see the mare, are lower areas. Well, yeah, those are all big impact basins filled in with mare, but not up to the brim. Okay. And on the far side, what you see are highlands. You know, you see these huge areas. So now if you go to the white area, and then you go to that blue area in the south on the far side, and measure that height difference, it's about 14 kilometers, okay, 14 kilometers. Here on Earth, if you go to Mount Everest and the Marianas Trench, the high and lowest points on Earth, it's about 11, okay, it's about 11. So there's enormous height difference on the moon. And in fact, this one area right there, this really low area, we call the South Pole Aitken Basin, okay? So this is an impact, and it's huge. It's 2,500 kilometers in diameter. It is the largest identifiable impact basin we see in the solar system, okay? So the moon really took one for the Earth that day, and that thing didn't make it to the Earth. It stopped at the moon, thank goodness, all right? But it blew one heck of a hole. And in fact, it blew most of that crust away. So what's really great about this area is it's either the lower crust or the upper mantle laying on the surface in that deep blue area called the South Pole Aitken Basin. Now, we can't even get to the mantle of the Earth. And so we don't really understand a lot. We don't have any physical samples of what the mantle looks like, and we'd like to do that. It's laying on the far side of the moon. Let's go get it. Okay, that's how the scientists think. Now, why is that important? Okay, it's all about how planets are put together. The mantle is under enormous pressure, and that changes the mineralogy. You know, that changes all kinds of things about the distribution of the atoms and the rocks, and based on the material that's in that mantle, to be crushed and be able to create a pressure that then supports the rest of the crust above it. And so that's a fundamental aspect of understanding how these terrestrial planets are put together by getting a mantle sample. Now, we call it the South Pole Aitken Basin. Yeah, it's a basin, so it's a big impact. And it goes from the South Pole to a very small crater called Aitken, okay? So that's where the name comes from. And we typically also call it SPA, South Pole Aitken. Okay, another fabulous set of observations from a different spacecraft, this is from Grail, gave us the thickness of the crust. Okay, this is what we wanted to know about. And we see on the near side, we can see the crust and we can compare it against the far side. And the crust on the far side is much thicker, 30 kilometers in some places, thicker crust on the far side than the near side. So any explanation of how the moon and the Earth were created has to take into account this dichotomy, okay, of this difference between heights, all right? In addition to that, because of the South Pole Aitken Basin impact occurred, why didn't the hot mantle pour in there? Why isn't that filled with the dark Mare? So one of the explanations we have is indeed the fact that the moon is tidally locked and dominated by the gravity of the Earth on the near side. Then the magma has a natural pull on the near side rather than the far side. So that's an element of the explanation, the thick crust and then the fact of the huge gravitational pull on the near side versus the far side, forcing the liquid mantle to primarily be on the near side. Okay, so now we have enough information that we can actually put together how the moon and Earth came together. And of course we had a whole bunch of theories. A bunch of them fell by the wayside fairly quickly. One was, the moon came by and we captured it. Okay, something that big, capturing it in orbit, and it's 60 Earth radii away, that's really tough. We could never get the dynamics to work out, so just forget that idea. And then so when we found out, well, the moon is much like the Earth, maybe the Earth, when it was created, was spinning so fast, a blob just popped out of it, okay, and created the moon. That has got so many problems, it was unbelievable. So you can forget that one. So there's one that it seems to really hit a lot of these things that we have found out about the Earth-Moon system. And of course, it really starts at the beginning. So there was a cloud 4.6 billion years ago in the position where the sun is today, and it was moving around the center of the galaxy. And we believe a nearby supernova went off, and the material from the supernova and the shock wave filtered through our cloud, and that began a process of condensation creating stars, okay, which then will create solar systems. Now in that cloud we estimate there's at least 200, maybe on the order of 250 stars were created out of our cloud. And so as things began to condense, and as I mentioned, everything's got some sort of angular momentum, what happens in this cloud as it moves around is it then starts creating a disk, okay? And it's in that disk then that you're accumulating enough dust, and the dust comes together, coagulates, if you will, and there's impacts, and then it reforms and gets to be bigger and bigger objects, and planets come from that process. And we can actually model some of that. There's some problems with it, but we can model some of that. So the basic then idea that seems to fit the most data is called the giant impact hypothesis, okay? And it is the proto-Earth, okay, and another object that probably formed close to our orbit, okay, because many of these things are forming independently. They're going to get together in collisions, in accretion, okay? And accretion is a violent process where two objects come together, collide, bust all up, but then reaccrete and create a larger object, okay? And so we believe this other object called Theia, okay, that's what we call it, hit the Earth. And Theia is about the size of Mars, okay? Now, about 25 or so years ago, our computers were good enough that we could actually model this. We could put in all the physics. We could run the computers for days and days on end and create a simulation. And how we do that is we break up every little piece of the Earth, and, the proto-Earth in Theia, into little bitty segments, and then we follow all the pressure and all the forces and changes on each one of those little cells. Okay, and so you see on the left that computer rendition, frame out of that computer rendition. Okay. But I'm going to show you the model. I'm going to show you the animation that's really the one that we believe happened. So here's Earth, proto-Earth, and here's Theia, and the impact. Okay, so this was an enormous impact. Now this big ball down at the bottom is the core of Theia. That comes in too. All right, so the Earth ends up with its core and most of the core material from Theia. The remaining material is just decimated all over the place, okay? And so it forms this disk around the Earth. So I'm going to move on to a static view here. So here's the Earth, and here's that disk of material around the Earth, and everything out to a certain limit falls on the Earth. And that limit we call the Roche limit. And beyond the Roche limit, things can come together and form new objects, okay? New spherical protoplanets, all right? And the reason why that limit is so important is if you're interior to that limit, the gravitational forces are so great, it pulls this object apart. The part of that object that's closest to the Earth feels higher gravitational pull than the other side, so it can't come together. The Earth's gravity keeps pulling it apart. But beyond that, it's weak enough that the object could actually start to coalesce, okay? And so it coalesces. The end result of the simulation is a really hot Earth and the Moon. But the Moon is only 3 Earth radii away, okay? So when you think about it then, the Earth has to be moving at 5 hours a day, because it's just like a ballerina that as the ballerina spins but then brings its arms out, begins to slow down, that we then go from this position of a 5-hour day with a very close moon to where the moon moves away 1.5 inches a year to get to the point of being 60 Earth radii away and the day on the Earth 24 hours. Okay? So the Earth is really hot, the moon is really hot, they begin to cool, and it's immediately tidally locked. Okay? From then on, it's going to be that way. That fits very nicely. Now, if you've ever seen the moon over the Capitol, it looks big. But if you can imagine this moon, if there was any life running around, which I seriously doubt in any way, in any form, this moon is 16 times the size of the moon that we have today. You know, it would dominate 1/3 of the sky. And then you'd be swimming around so fast at 5 hours a day, you'd hardly have time to look at it. But, you know, so this is really a fantastic dynamical interaction that's going on, and it fits the data, all right? So the other aspect of that is, okay, all that seems to look good. You know, we can get the age of the Earth and the moon. We can get the fact that they're both same material, made in pretty much the same kind of orbits, came together and then merged their materials, okay? That all works. And tidally locked, moving away from the, all the things that we found from Apollo. This model looks great. Well, what about the thick crust on the back, okay? So what may be happening is, much like the Earth-Theia concept, another moon may be created somewhere else in the cloud and then impacts our moon and then lays over that far side and creates that thick crust. So that's theory one. We don't know if that's true or not. By going back to the moon and looking at the samples and the ages of those, we can tease that apart. The other theory that's come up actually comes from the group of scientists. Since I see Paul Hertz here, the head of astrophysics, I want to throw a good shout out to Paul in the astrophysics area, because the next big theory that we think may have happened actually comes from looking at exoplanets, okay? And so the idea is the Earth is so hot that it's actually heating the near side of the moon, and since the moon is locked, tidally locked, you're just wasting away, okay, the moon. And so that material then is flowing off, maybe losing it, or accumulating also on the far side, creating that thicker crust. Now, that comes from observations of stars and close planets, where the modeling seems to indicate that that's happening with exoplanets. So that theory actually came out of the astrophysics group, which is wonderful, the ability to think about these things across these disciplines. Now here is another really great observation of the moon. It's actually taken by Cassini on its way out to Saturn. Now we also had another instrument at the moon called the Moon Mineralogy Mapper. And this is a colored image, and it's from the infrared. This is in light you can't see, okay? And what it tells us, these huge differences in color, are really all about the mineralogy that's laying on the surface of the moon. And you can see it's just heterogeneous. You know, there's stuff, all kinds of stuff laying in different places, okay? This gives us really a wonderful opportunity to go to different places on the moon now with this data to be able to bring back material from that initial impactor to understand much more about where that stuff was generated and how the heck it got to the moon. And so now with our age dating capability, we can get a good idea, it's not a complete idea because we haven't been everywhere, of the size of these basins and how old they are. And what we found out when we looked at this is there's an epoch, it's at about 4 to 3.8 billion years ago, where a new bombardment occurred. This was shocking. Now, planetary scientists knew about this for a long time. We didn't talk about it much, but it's really important. So what happened is the moon came together, all this bombardment happened, then everything seemed to settle down, there'd be some bombardments going on, and then all of a sudden the moon was just hammered over and over again for several hundred million years. We call that the late heavy bombardment. And that comes from age dating the samples we brought back. And these are the basins that are created during that time period, okay? These are younger than the others. And so how the heck did that happen? So we think we now know. We think we now know. And it started by a group of scientists, planetary scientists, in the mid-2000s. Several were in France. They were on sabbatical. They had a little workshop where they were the top modelers of the world. They were using their computer analysis to be able now not to just create the Earth and the Moon, but all the planets, okay? And so they were running their models. And they were trying to create a solar system that looks like this, you know, where you got Jupiter, Saturn, Uranus, and Neptune at these distances away from the sun, okay? So you got Jupiter at 5, Saturn at 10, and then 20, and then 30 in terms of astronomical units away from the sun. And so they'd run, you know, they start out with little seeds and have a lot of cloud material, and then they'd let their model run. They would run it for 4.5 billion years, and they couldn't make those outer planets. Couldn't make them. But we knew they're there. They knew they got made, and we know they got made early on, maybe in the first 10 or 20 million years. Okay? So what was the problem? Well, a group of them went drinking. You know, it's Nice, France. You know, they went out and had some wine. That's great. So while they're talking about, you know, well, is the physics there? You know, what, you know, none of them couldn't get it. So are they missing physics? So they went through everything they could think of. Okay, we think we got all the physics modeled, so can't be that. And so one of them said, well, why don't we figure out how to create these planets anyway? What do we have to do that? And another one said, well, the only way to do that is move them in. If we move them in, I think we can create them, okay? And so the initial start of their model has these giant planets at different locations than where they are today, okay? Let's just get them created. That was what they were trying to do. Very simple idea. But what came out of that was revolutionary, okay? Now, they had the ability to run their models for 4.5 billion years. And so they could get them started and run them, okay? And so what they found out when they moved these planets in, they started running the models, they formed right away. They got them to be formed. But they also ran their models. So what you're seeing on, in this panel is looking down at the solar system where the red orbit is Jupiter, and then you got Saturn, Uranus, Neptune, and then you have a debris field material that we call the Kuiper Belt. These are ices. These are the remnants of the outer part of our solar system that are accreting and becoming smaller objects, but they're really got all kinds of beautiful volatiles in it and plenty of water. Time the rocks told us of the late heavy bombardment. Okay? Completely independent set of observations. And I'll mention one other thing. When we go back and we look at the life record on Earth, life started at the end of the late heavy bombardment at about 3.8 billion years. And so did this material we bring in help seed life to this planet? Okay? The answer to that is laying on the surface of the moon in terms of getting the ages and dates right and understanding this giant planet migration. So here's the basic results. The top panel, we start out with that. Then Jupiter pushes these guys around, and then we end up with the current solar system. Now there's variations of this. And it turns out if you add another planet about the size of Neptune right after Saturn, that one gets ejected deep or maybe even out of the solar system. And maybe that's planet 9. But the modeling supports it. The modeling supports it. Now this is phenomenal when you think about it. Something the size of Jupiter, 300 times the mass of the Earth. If it was a fishbowl, you could put 1,000 Earths in it. Jupiter's truly a magnificently huge body, and yet it moved. It's in a different place today than when it was created, and it pushed the other planets around too. All right, now what we want to do is also look at one of the observations that is an absolute game changer, and it's in the poles. And it starts by taking a good look at the characteristic of the craters in this area. So this is the South Pole. You know, we've tipped the moon. Now we're looking down at the South Pole, and what we're going to do is we're going to, as if we have a spacecraft hovering it, we're going to follow the moon around the Earth. And when we follow the moon around the Earth, all the shadows change, because indeed that sun angle changes. You know, a lot of people say, oh, we have a near side of the moon and then we have the dark side of the moon. That's not correct. We have a far side of the moon, which also goes through the same lighting phases as the near side, okay? And so this tells us, when we look at it closely, there are craters that are permanently shadowed. So this frame gives us an overview of those shadows, and it shows us a number of craters that never see the sun, never see the sunlight. And then when we look at the temperatures, this is also from LRO data, we see these are some of the coldest places in the solar system. Now what's really fantastic about these observations is that we're finding out by flying over these and making certain types of measurements that there's water, okay? There's water in these permanently shadowed areas. It's hiding in these areas. It's been driven into these areas through a variety of processes. We call that a cold trap. It's basically thermodynamics. Things that are hot want to migrate to things that are cold. And so if you have water in the area, somehow it moves there. Well, how you get water is you bring in comets and impact the moon, and some of the water goes into the permanently shadowed areas. Asteroids have plenty of water. They hit the moon. Some of that goes into the permanently shadowed areas. So over the 4.6 billion years, the moon has been accumulating water. And then another spectacular discovery happened recently from the LADEE spacecraft. Okay? So if we see this graph in the upper area, it's measuring water content over time. And we see these peaks. So as LADEE's flying around the moon, all of a sudden, the moon is emitting water everywhere. It's flying through a cloud of water. And then it dissipates, and then a little while later, a new cloud comes out. Well, it's not that the moon is moving through clouds of water. The water is coming from the moon. So how is that happening? These occur during times of meteor showers. Okay? And the real big peak here in 2013 lines up perfectly with the Geminids. And so micrometeors are hammering the moon. So that top layer, which is being hammered, that's all desiccated because that water left a long time ago. You have to penetrate much deeper, create a shock wave that goes down almost 10 feet, we believe. That liberates the water, okay? And in fact, Laddie discovered in some of these peaks times of meteor showers that we didn't even recognize before because of this water atmosphere that's created on the moon. Where does this water go? Well, some of it gets ionized, swept away from the solar wind, but others end up going into the cold trap. And that's in the permanently shadowed craters. Now, I just talked about a couple of the science things. These are transformational science. By going back to the moon, we can tease out what's going on. We can get our chronometer right, understand the entire bombardment history of the solar system. We can look at the late heavy bombardment, understand what happened, how it happened, when it happened. We can go and enter these permanently shadowed regions and taste the water. Some of these watered areas may also have other volatiles, like from comets. And so we want to take samples that we can really analyze to determine what the origin of that water is. Other things we didn't talk about is the history of the sun, and therefore the solar wind is laying on the far side of the moon. It's literally impacted the moon. And we can go get cores, and we can determine the history of the sun. We can determine if the coronal mass ejections are bigger in the past than they are today, giving us an idea if they'll be bigger in the future, and whether we should be worried about space weather or not. Some of those answers are on the far side of the moon. We want to understand how big that core is. We don't think there's much of a core left. The Apollo data only had certain limits to it, and we didn't really get a good seismic measurement all the way down to the core. And then on the far side, it's so radio quiet, it opens up a new wavelength regime. Here on Earth, we have so much radio interference, there's an entire radio regime that we have not been able to look at the universe in because of the confusion that's going on with anything that we would do today here on Earth. But on the far side of the moon, it would be radio quiet. And so this brings us to Space Directive 1. We have plenty to do on the moon, transformational science. And now we have a direction, and that directive says going from Moon to Mars in a sustainable way, working with partners, both commercial partners and our international partners. And oh, by the way, we want the first woman and the next man to step foot. I think that's great too, on the southern pole rather, of the moon. So how are we going to do this? Our current plans, since we also have the directive to be able to do that by 2024, we created a plan to be able to do that. And we start out with indeed working with our commercial partners, and once again, with our precursors, getting down to the surface, going to areas where we can get samples, but in particular, going to the South Pole and doing some what we call ground truth, getting some cores, looking at, at the water concentrations, and really start in the next several years to do that. Now we have a group of commercial vendors that we're working with, and here are the 9, okay? And most recently, 3 of them now are committed to launch and land on the moon, 2 in July 22 and 1 in September 21. And so this is really a great first start. And then, of course, what we want to be able to do that is several times a year from then on. And the next thing that's happening is we're making great progress developing the Space Launch System. And with that, of course, that's the Orion capsule that will carry the astronauts. And this particular system then will go to the moon. The first flight is scheduled for late in 2020, late next year, to actually launch, figure 8 around the moon, come back, uncrewed, really shake it out, and then that enables us a year or two later to then go back to the moon in a way with the SLS and the Orion capsule to then orbit the moon and come back. So that'll be our first foray. And then in the meantime, we're using a variety of launch systems to be able to get up to space what we call elements of a small space station we call Gateway. So this is going to have solar electric propulsion. It's going to have a mini habitat module. And then, of course, we're also going to continue to land larger things down on the surface of the moon. And then finally, as we get into the 2024 era, we have one big push. And the big push then brings the lunar descent and ascent module, and it allows then from the Gateway for us to get down to the surface, down indeed to the South Pole, and then have the first woman and the next man step down on the surface in 2024. So what happens after that? Well, we're currently planning a whole series of other missions that will take advantage not only of the science that we want to do, but also in a concept that we call sustainability, leveraging the equipment that's there and begin to build the capability to sustain humans on the surface of the moon, and in doing it in a way that allows us to tap this water. The water that we find in the South Pole and the North Pole is a game changer. It's anywhere between 100 to 200 million tons of water, and that might be an underestimate. We'll only know once we crawl in there and take a look at it. We can take that water, tease it out, create rocket fuel, hydrogen and oxygen. Of course, we can breathe the oxygen, and water, we can drink the water. H2O is H2O, whether it's here on the moon or on Mars. That's water. And so we have opportunities also to do some mining. There's a lot of precious group metals in this particular area, in particular in that South Pole Aitken Basin. And the whole idea then is we'll use this infrastructure to practice what we need to do and then go to Mars. And that would be the next step in the late 2030s and into the 2040s. Thank you very much.
Thank you, Dr. Green.
My pleasure.
And thank you to Aerojet Rocketdyne for their support.
Thank you.
And thank you all for your time and for joining us this evening and for our series next year as well. Please exit through the doors at the top of the theater on either side. Have a wonderful evening. Thank you so much for coming.
Right. Rocketdyne and ULA, thank you so much. Right, indeed.